time did it start? The contest start versus the Eclipse time?
So the contest started about 2 hours before partial eclipse hit the United States, and it ended about 2 hours after partial eclipse hit the United States. Yes?
It would be interesting to see the plots for the new amateur bands in LF region. That would be very, very narrow.
Yes, it will be.
Yeah, obviously it'll be enhanced there too, but also above 30 megahertz. Did you take any measurements up there?
I haven't focused on that. I know that some of these systems do listen above 30 megahertz, but that wasn't what I was focusing on.
Yeah. I doubt there would be really any enhancement at all.
I mean, you can see right here that once you get above 20 meters, you know, the plasma frequency was already too low to support 15 or 10 meters. So I didn't look above that either. But for the VLF stuff, that will be very interesting. One of my friends, his name is Bill Lyles, NQ6Z, I think. I'll have to double check the call. But he's very interested in the low frequency and the VLF response of the ionosphere to the eclipse.
They would have beacons operating too, so to make it easier.
Yes, yes. So, so this year he was working with some researchers who used some of the military VLF transmitters, and they were listening to those signals. And he's hoping for the next eclipse to make use of the new amateur bands. So that'll be very interesting. Yes?
Do you have a graph of the plasma density changes as the eclipse went through?
I don't here. Yes, here I'm only showing the ham radio data, but that is available from other people as well. And some very interesting papers that have just come out from the MIT Haystack Observatory, they use GPS total electron content. So how many people know that you can actually measure the amount of electrons between here and a GPS satellite with a receiver, a GPS receiver? Did you know that? Yeah, it's really cool. You need a special GPS receiver to do this. So the one in your car isn't going to be able to do it. Right? No. So the problem is that to make these GPS TEC measurements, total electron content measurements, is you have to measure the delay of the radio frequency, the phase delay between two different radio frequencies going through the ionosphere. And by looking at the delay between the two frequencies, you can back out the number of electrons between the transmitter and receiver. So your cell phones and the GPS receivers you have in your car, they're only single frequency GPS receivers. But if you buy more expensive equipment that's designed for this, you can get dual frequency GPS receivers that listen I think around 1200 and like 1500 megahertz, and they're able to compute the total electron content. And then you're able to make beautiful maps of the ionosphere. And that's actually one of the things I'm working with right now. I'm trying to take what I have here, I'm trying to compare it to some of the features I see in these total electron content maps, and I'm trying to do a better job of explaining what I'm seeing here based on there and vice versa. So that's what I'm working on right now. Yeah. One more plot before we end. And this, I also created a control set of data just off using data I downloaded from the Reverse Beacon Network website. And that's this. So this is RBN data plus and minus 15 days from the eclipse. So you can see what, say, 20-meter behavior looks like normally in August on the RBN. So this is, again, your dB, your signal-to-noise ratio. It's fairly flat. You can see some of the diurnal variations in there. And you can also see what ranges you expect to hear typically from the RBN, from all these RBN receivers for 20 meters, 40 meters, 80 meters, 160. And you can see very clearly that the typical behavior does not include that notch in the middle of the day on 20 meters, or the enhancements in the middle of the day on 40 meters, 80 meters, and 160 meters. So I can flip between these. and you can see some of the differences. Now, here's a trivia question about the control data set. I threw out Wednesdays, so this control data set does not include any Wednesdays. Does anyone have any idea why that might be?
Because it's hump day?
No? No. Every Wednesday in this control data set did. What?
Your day off?
It was not my day off. Yes.
Because there's 365 days in the year, Wednesday happened to have that extra Wednesday in the year.
No? Okay, I'll give you a hint. So who's are there any CW operators in here? Oh, I see a few people shyly putting their hands up. Does anyone know about the CW ops? Oh, yeah? What do CW ops do on Wednesdays? What?
Sprint.
They have these 3 little sprints. There are these short 3 one-hour contests every Wednesday. And since I'm looking at all CW data, I was looking at the control data set, and I'm expecting to see this nice, relatively flat-looking pattern here. And I see around the same time every day, I'm like, there's a really big bright red blotch there. I'm like, it's about an hour long. I'm like, that's kind of strange. Why is that? So I took my control data set, instead of doing it all the days on one plot like this, I did it for every single day so I could look at every day individually. I noticed every Wednesday had one of those red blotches, and it corresponded exactly with when the CW ops have their contests. So I thought this gave us a better, a better control data set by just taking that extra bit out there. I don't think it was very representative of what's normally happening. But those are some of the real challenges with working with the ham radio data. I showed you Steve Ryer's frequency measurement test types of measurements of WWV. And that's really nice to work with because I can go to Steve, I can say, okay, what type of antenna did you use? What are the limitations of your equipment? And I can get really good numbers to be able to put error bars on things and really understand the experimental setup. And out of that, hopefully, be able to detect new things. Because a lot of what we're seeing here, this is kind of what we expect to see, right? We expected the Eclipse to cause a drop-off in 20 meters and cause enhancements in the lower bands, which is great. But now to push it, we've known that for a long time, but now to push it to the next level, how do we get that new science out? And that turns out to be really challenging with things like RBN data because it's all quasi-random. How do we actually prove that it's this thing and not just the fact that there's a whole bunch of extra people on the East Coast and not the West Coast, or things like that. So those are just some of the challenges we're facing. But it's still, you get some really neat looking plots. We have some really neat looking things, and some of the, by having the data that all of you and the ham radio community provided, that's really given us the opportunity to look and ask, what are some of the new things? If we didn't have the ham radio community's participation, I wouldn't have Steve WA9VNJ. I wouldn't have his data to look at that. Oh, what is that little S curve in the middle? And so that's really giving us new opportunities to look at things that we haven't really seen before. So that's really cool. All right. So in conclusion, this was run by the Ham Radio Sciences Investigation. It's an organization I started along with some friends to allow university researchers and professional researchers to collaborate with the amateur radio community in scientific investigations. And from this Eclipse party, which many of you participated in, we have clear evidence of the atmospheric density reductions. We could see the Doppler shift showing a lengthening and shortening of the 10 megahertz paths from Steve Ryer's measurements. We could see reduction in the 14 megahertz SNRs and path lengths in the RBN data, and we could also see increased SNR and path lengths in the 160 through 40 meter 1.8, 3.5, 7 megahertz RBN, signal-to-noise ratio, and path length data. And so, of course, that implies there was a reduced critical frequency during the eclipse and a reduced D-region absorption. And so for future work, we hope to use this data set and have these data sets around to do further testing and validation of ray trace models, like the ray trace model I showed you at the beginning, ionospheric models. We want to develop new techniques for using ham radio data to characterize the ionosphere and try to understand things. And we might want to look for some more localized effects. So, we're showing things on a big scale right now. How can we take this data and understand things on a smaller scale? Can we learn something new from the ionosphere? So I have many people to thank. Every person in this room who participated in the Solar Eclipse QSO Party, thank you very much. This has presented, tremendously interesting data for us to look at. And these are just some of the people. I'm sure there are more people than on this list that have, given me ideas or input or have participated in experiments. All sorts of work has gone into this. And so I also want to just say, I had this slide on a few weeks ago as an advertisement, but now it's kind of a wrap-up. We had a few people who came to our HamSci workshop at the New Jersey Institute of Technology a few weeks ago. So I know Ed and Tom were there, and I think Randy was there as well. And so it was really neat to have you come out there. And we had people from all over the world. We had people from the United Kingdom and Canada and NASA, Marshall, and MIT Haystack, and Johns Hopkins Applied Physics Lab, and Clemson, all come here, some of whom were, most of them were hams and scientists. Most of them, only a few were not. But it was really neat to see so many people come together. And now what's neat is, even though this is done, if you go to hamsci.org now, most of the PDFs from that meeting are now posted online. So not all of them. I'm going to try and get track down more of them to get them posted, but most of those PDFs are posted online. Just go to hamsci.org. You'll see the link for the workshop page. Just click View Agenda, and you should be able to download those PDFs and kind of get a flavor of what was talked about. So with that, thank you very much for your time. It was a pleasure, and I'll be happy to take a few questions. Yes?
Curious, how many hours have you devoted to this?
I have no idea. I have no idea. Right, I've been working on this for a couple years now, and I mean, this is basically what I'm doing for a job right now, trying to get information out of this data. So yes.
So I mean, you're into the data at this moment. So maybe this answer isn't relevant, but what as you've gone through this, and you tried to show us whatever you could, but what really, like, was there anything shocking here to you and said, wow, I didn't know that was going to happen?
I think, I think some of these smaller scale features, like that little S curve in there, that's something that I wasn't expecting, and that's a little puzzling. I think what's cool, and this is what I've been working on today, I could see that feature in both Steve's data and in the GPS TEC maps from MIT Haystack. And so I was actually on a teleconference day with some of the MIT Haystack people and working with my good friend Dr. Mary Lou West, KC2NMC, and we were like trying to figure out, okay, how does this actually line up with the GPS TEC stuff? And the person at MIT Haystack, Anthea Coster, she's like, yeah, I'm not sure, like maybe this is just an artifact of my processing, but using the GPS TEC. But what's neat is because we have the ham radio observations that also show the similar feature, we're like, okay, well, we've seen this feature in both the GPS TEC and we've seen it independently in the ham radio data set. So that means it's probably not an artifact because we're seeing it from two completely different ways of looking at the same thing. And so that's that's I think a real power of this community, is we're able to go provide data that would help these other projects that otherwise people might be saying, well, is that real or is it not? Well, yeah, we see it too. So yeah, it puts good evidence behind it. Yes?
Other eclipses coming up? Are you planning to do similar?
Yes, there are other eclipses coming up. There's one in 2024, and people are starting to think about that. So I know some people at Case Western Reserve University are starting to plan for that. My friend Bill Lyles, who I talked about before, he's working on the VLF stuff. He's actually working on a project for an Eclipse in India in just a couple years because he wants to do that again before he brings it back to the United States in 2024. And so I'm kind of thinking about all this stuff, and I'm also being like, all right, I'm still working over here. So yes, there is stuff coming up in the future. It's still in planning, and where hopefully the things that we learn from here are going to guide what we do in the future. Okay. Yes.
Do you think, if you looked at that swirl on the first couple slides you showed, do you think that would have any bearing on that S you saw in
the swirl on the first?
You see the red kind of swirl around the blue at one point?
Oh, actually, it's a possibility. So I actually was looking at that as a possibility today. So am I 100% sure? No, but it is one part of the equation that we were looking at. Yes?
Have you looked comparatively at historical data for what the ionosphere looked like 30 years ago compared to what it looks like now? So to see if this experiment would have taken place during a previous solar eclipse, would the data have been skewed or the same? So I'm going to tell you where I'm going. So this might be more of a Mythbusters question. When I was a kid, people used to say that the aerosols were destroying the ionosphere. I don't know if that's true or not. But I'm wondering if changes in sociology and society might have affected the ionosphere so that it looks like what it does today during an eclipse versus what it might have looked at in the past.
So I've looked at this somewhat. I can't say I haven't looked at it all, but I haven't done an in-depth study of it. I guess, so to answer your question, there is definitely going to be a difference in the ionosphere of this eclipse versus one, say, 30 years ago. And from some of the things are from things that we just know as hams. We know that there's an 11-year sunspot cycle, right? That drives, ionization, or is correlated with ionization of the ionosphere. So if you have an eclipse at a different part of the sunspot cycle than now, you're going to see something different. We also know that if you look at the number of sunspots over a longer period of time, we know that not all sunspot cycles are created equal. So some sunspot cycles are stronger, some are weaker. And so, yes, if you look back even at the same point in an 11-year sunspot cycle, you are going to have a different ionosphere that day than you do today. You also have, yes, you can also have other impacts from maybe even climate change or some of these other things. So my PhD work was done looking at these things called traveling ionospheric disturbances, which I talked about before. And I was able to use the super-darn radars to link certain types of traveling ionospheric disturbances to the polar vortex. And I saw that when you had a strong polar vortex, you had a lot of traveling ionospheric disturbances in, say, late fall and winter. And when the polar vortex breaks up during what's called sudden stratospheric warming, the traveling ionospheric disturbances go away. And so, again, we've been seeing more breakups of the polar vortex recently. So yes, so there's many different things. You can also have even different parts of the world. The background magnetic field, we know that the north magnetic pole moves with time and is also not centered right at the geographic pole. It's offset a bit. And so that actually causes interesting features in the ionosphere too. So if you have an eclipse here at the mid-latitude United States, it's going to be different from an eclipse in the polar region, and it's going to be different from an eclipse at, say, in India or someplace that's closer to the geomagnetic equator. So all of these things. And you can have, if you look in previous eclipse literature, one of the things I do look at first is what were the background geomagnetic conditions? Was there a solar storm? Was there a geomagnetic storm? Was KP high? Was it low? So yeah, comparing one eclipse to another, they all have their own subtle. Any more questions? I'll be around during the break and things, so thank you so much.
Nathaniel, thanks, okay, as always.
Thank you,
Okay,
Ed.
for a really great presentation. As always, we have a plaque, okay, a certificate of recognition for your presentation. You're the first person in 3 years of doing programs that this is the second time
Wow.
we're giving you one. So
Thank you so much.
congratulations there. But
Thank you.
wait, there's more. Because anyone who's come back twice does deserve a second gift. We have one of our QSLs from our Great Falls National Historical Park. This way we can really fill your office wall.
Thank you so
over
much.
in Hoboken. And then lastly, courtesy of Judith and Fred, we heard you have a sweet tooth.
Yes.
So we have some black and white cookies for
Oh,
you.
thank
to take home
you.
as well. So
Thank you very
thank you
much.
all. This is a rare opportunity for
Thank
this
you.
club to have a presentation like this. So thank you all. Really great turnout.
Thank
as
you
well.
so much.
Thanks much.
Thank you. Thanks, Ed. That was really nice.
That's great. Thank you.
You're welcome.
So we'll stay in touch.
Yeah.